I'm very glad to introduce our second keynote of the day. So we come back to robotics. Jessica accepted our invitation very quickly, to be honest, and with great pleasure. So Jessica Burgner-Kahrs is a multi-associate professor, let's say, with the departments of mathematical and computational sciences, computer science, and mechanical and industrial engineering. She's also the founding director of the Continuum Robotics Laboratory and associate director of the Robotics Institute, all at the University of Toronto in Canada. From 2013 to 19, she was with the Leibniz University in Hanover in Germany, where we had very much pleasure working with a very brilliant team. And she was from 2010 to 12 with Vanderbilt University in the US, and she received her diploma in 2006 and PhD in 2010, both in computer science from Karlsruhe Institute of Technology in Germany too. Jessica's research focuses on continuum robotics, and in particular on their design, modeling, planning, control, as well as human-robot interaction. And her fundamental robotic research is driven by applications in minimally invasive surgery, which explains in part her presence with us today, but also in maintenance, repair, and operations. In 2015, her research was recognized with the Heinz Meyer Leibniz Prize, the lower section Science Award in the category Young Researcher, and she was entitled Young Researcher of the Year in 2015. The Berlin-Brandenburg Academy of Sciences awarded her the Engineering Science Prize in 2016, and she was also elected as one of the top 40 under 40 in the category Science and Society in 3 years in a row, from 2015 to 17. By the business magazine Capital, and still counting, but also in 2019, Jessica was elected as Young Global Leader from the World Economic Forum. Her talk today is entitled Advances in Continuum Robotics for Medical Interventions. And in this talk, Jessica will provide an overview on advancements in continuum robotics research and focus on novel features, such as drastically increased motion capabilities through three main topics: extensibility, adjustable stiffness through scale sheets, and higher accuracy through parallel structures. Jessica, I'm very delighted to hand you over the presentation, so please, you can share your screen.
Thank you so much, Taha, for your kind introduction. Bonjour, everyone. Welcome. I was really happy to accept this invitation when Taha and Jocelyn emailed me earlier this year. Back at that time, I was actually hoping to be there in person today. That would have also meant that I could be in Germany for Christmas. Still in Canada, so I guess that didn't work out, as many things this year were very different from, I guess, what we all assumed it to be. COVID is real, so I hope you're all safe. And while certainly virtual meetings are not the same, I'm very honored to speak here today to all of you. I have been quickly going over the attendees, and I see very many familiar names, so that's great. And while I'm not here in person in France, well, for me it's 9 o'clock in the morning in Canada, so bear with me. I haven't been able to follow along the meeting your morning, but I'm hopefully going to stay until noon and see all the great things that you have been doing. I also wanted to congratulate you on the amazing results and things that you have been accomplishing in the Computer-Assisted Medical Interventions Laboratory of Excellence. I have seen that you have been extended for 5 more years, so that's awesome. So congratulations, that's great. I must say I had the greatest postdocs. Taha was the first one, and currently I have Quentin Perron working with me here in Toronto, and actually the greatest postdocs I've worked with are from France. So it's dear at my heart to connect with the French research community. Before I dig into the talk, I would like to give you an update on where I am. You heard already I switched countries again 2 years ago. So many of you will probably know me as a professor in Germany. But I left Leibniz University Hanover in March 2019 as I got this great opportunity to become a part of the University of Toronto. And as a side note, this was actually soon after Taha left the lab. Things were just not the same anymore, so I figured I might as well go. So yeah, now I'm here in Toronto. You can see here on that slide, it's actually a huge campus. The University of Toronto has 3 campuses that span the greater Toronto area. In the center, you see our beautiful campus that was established in 1827. So that's downtown Toronto. You might recognize the CN Tower, which is one of the landmarks of Toronto. And then there's these 2 suburban campuses, which are have been established later in the in the 60s. But they are beautiful. Like, I'm located on this campus over here in Mississauga. It's the neighbor city of Toronto. Actually, 2 million people are living there, so it's not that small, even though you might have never heard of it. So it's a beautiful campus enclosed in the woods. There's geese and deers running around campus. So it's really beautiful. Taha was fortunate enough to visit us last year after ICRA, when we were all still able to travel. So yeah, it's really been great to work at the #1 university in Canada. It's also in the global top 20, so it's remarkable. It's a leading institution. And while Toronto in itself was very intriguing for me to come here, it's really also, I came for the people. Like, just on this slide, I am showing all the awesome researchers that are working on robotics-related topics at the University of Toronto. So being among so many roboticists was clearly driving me here. And that's remarkable. Many of these faces here are actually researchers in engineering, and just a few of them are in computer science. And so one of my, missions or my mandate in coming here is to establish robotics also in teaching and research in the computer science department. And that, to me, was really intriguing to move country again. So just last year, we have established the University of Toronto Robotics Institute in 2019, which I'm fortunate enough to be co-directing. And it's our mandate to build Canada's most versatile robotics talent network. We are focusing on 3 themes. One is core robotics fundamentals in terms of hardware technology and algorithms. The second is domain-specific expertise. This is where healthcare, also mobility and manufacturing comes in. And then lastly, also to be globally connected and becoming a leading center of excellence. And that all to be inspired by becoming innovators for robots for a better world. So I'm really happy to talk to you all today and connect to you all. So that was the advertisement part, I guess, for Toronto. Let's come back to the talk, coming back to what I'm here for today. I would like to take a moment with all of you to think about the following question. How does a surgical robot look like? Just think about your mental image of how a surgical robot looks like. I bet that most of you have probably been thinking about the Da Vinci robot from Intuitive Surgical. Most of you have probably seen it, have worked with this amazing piece of hardware. The Da Vinci robot system has been deployed in, I think, as of now, it's 67 countries. I just looked this up yesterday. They completed about 7.2 million procedures worldwide with over 5,500 systems installed. So the Da Vinci robot is clearly the lion in the room when we think about surgical robotics. And it has been a driving force for acceptance of surgical robots in the broader society. And many people are asking about having a robot operating them. I'm teaching the Introduction to Robotics course, and I just had a student that was super excited telling me that he was actually operated with a robot. So he had a gallbladder removal using the Da Vinci robot, and he was so excited that it made him take the robotics course at the university. So the Da Vinci robot really helped us as researchers, I guess, to get surgical robotics being more at the state of minds. When we look at this robot from an engineering perspective, what we see is that these robot arms are, well, I guess, simple or conventional serial robot arms, right? It's a bunch of revolute joints and a prismatic joint at the tip here that can drive the instruments back and forth. The instruments of the Da Vinci robot are really what helps the surgeon to do their laparoscopic interventions much better. They are super dexterous, have all these like high sophisticated wrists and stuff. But I really wanted to focus on that robot part back here. Because when we look at this Da Vinci robot, but also at many of the other surgical robot systems that are out there, there's this one fact that I find interesting, which is that most of these robot arms are actually very much looking like what we know from industrial robotics, from automation. Like it's the same principles that we apply in surgical robotics. And that was actually also how I got into surgical robotics back at Karlsruhe Institute of Technology, how it all started, I suppose. So when I started my PhD back in 2006, I also had this industrial robot arm. It was a Stoibli RX90 robot at that time, available to me in the lab. And then my PhD thesis was focusing on robot-assisted laser osteotomy. So I was using a carbon dioxide laser, I think it was 100 watts, so it was pretty powerful. That was guided through this mirror arm here. At the tip of the robot, there was a little mirror deflecting device, a MEMS device, to get the laser deflected on the surface, such that I was able to cut bone in various shapes. It was all pre-planned using this robot system. So that's how it started. And if you have been following along social media this year, you have probably been seeing there's also this how it's going. It's interesting to see, like when I finished this thesis in 2010, I would have never thought that this goes somewhere, because you see the setup is enormous and it's huge, and it wasn't very practical, I suppose, from a clinical standpoint to have that all in the operating room. But funny enough, AOT in Switzerland took on this idea, advanced it quite a bit, and they have now built this rather small and more delicate robot. It's a collaborative robot. I think it's based on the KUKA lightweight robot. And they have integrated a laser device right at the end effector, which is doing a cold ablation, so much less less cumbersome as the setup that I used earlier. And I think they just did their first in-human study last year. So it's interesting to see that this concept idea of cutting bone with a laser system has been used in a surgical robot system too. Yet it's still this serial robot arm, right? And I still want to continue talking about this serial arm robot system and why this might not be, at least from my understanding, the best idea for surgery. Because when I think of surgery, also in my collaborations with clinicians, what they usually tell me is that there are so many things that they cannot do with their classical instruments, right? So there are all these locations that are really hard to reach within our body. So for example, the center of our brain, like reaching the pituitary gland, for example, is really tough because it's really located in the middle, and we'd rather open the skull widely to approach it. We might go through the nose or somewhere, but it's really challenging to get there. And the same is true for like deeper seated lesions within the lung. Could also think about reaching the kidneys on a non-invasive route. Like all these tasks that are characterized by having these nonlinear trajectories leading to them, that are hard to reach, that are only reachable on very tortuous curvilinear path, or that are characterized by being seated within a lot of delicate anatomical constraints, a lot of nerves, such that it's really hard to reach them. And so in many of those, I would really like to see a surgical robot that is able to perform a keyhole approach, right? That would be able to reach this with minimum opening of the body, probably through a natural route even. And then having instruments at hand which could allow to access those areas and still be manipulability, has still high manipulability and dexterity at the surgical side. That is almost contradicting, being like really small and dexterous yet compliant and strong. So this has always been on the top of my head. So And being an enthusiast for a lot of animals as well, like I really draw a lot of inspiration from what I see in the animal kingdom in my robotics research. So working on continuum robots means that I am trying to build robots that have no rigid links or joints, that are not composed like the classical serial arm manipulators or parallel robots that we see. So I'm trying to not rely on any revolute joint concatenations or prismatic joints. And when you look at the animal kingdom, you can see that there are actually very many examples of these small yet dexterous, let's call it devices that animals have at hand. One and foremost, the elephant trunk. When you think of what an elephant trunk can do, it's quite remarkable. Like, not only can they use it, not only is it their nose, right? But they can also reach very hard to reach places. They can use it as a weapon even. They can use this to draw water in or to grab food. And that's quite remarkable. Same is true for the anteater tongue. It's like the longest tongue in the animal kingdom. It's up to 30 to 40 centimeters long for the anteater to get to termites and ants at deep-seated locations, for example, within a tree. So these are great examples that are really showcasing some of those abilities that I feel physicians and surgeons would really like to see in instruments when they would like to do keyhole access surgery. And interestingly, like, surgeons are very used to using continuous devices, right? So, for example, catheters, and particularly catheter steering robots, are actually continuum robots. And they are regularly used, like either manually deployed or robotically steered, like these two here from Hansen Medical, now Auris Health, and the Corindus system, where the catheter is actually put on these two actuators, which can linearly translate the catheter, pushing it back and forth, and also actuate the tip of the catheter. Is usually bending in a plane or in two planes. So having these catheters being robotically steered, they qualify as being termed a continuum robot with low degrees of freedom, but still, so they can be used for cardiovascular interventions. And it's great because they can be teleoperated, so the physician can be outside of the room, because these catheterizations are usually performed under fluoroscopy, and so saving the surgeon from the radiation is really a great cause for making use of a robotically steered catheter. Another example of a continuum robot that is actually used are these newer systems on the market, like these bronchoscopy steering robots that have been developed both by Auris Health and also by Intuitive Surgical. So it's also continuum robots with not so many degrees of freedom. So it's bending in the plane, you can rotate it and then steer it through the bronchi in the lung, for example, to access the periphery and stage a tumor or perform diagnosis. So while these are all continuum robots, and you might say, oh, that's great, so we have this ability to reach these deep-seated locations, at least in those areas, right? Everything that we can reach through the vasculature and everything that we can reach through the bronchi is somehow done. So maybe there's not that much need for research. But the downside is that these continuum robots, if you want to call them that way, are really relying on these pathways for steering, right? So a catheter, also a bronchoscope, is in itself a limp device, right? If I would just hold it like that, it would just fall down. So it really relies on the interaction forces and on this natural pathway to be there. So as long as I'm in this tubular structure, it's fine. I can just bend the tip and can achieve steering through that. So that's not really all the dexterity that I would like to see. Now, I asked you that question in the beginning, how does a surgical robot look like? Now, when I think of a surgical robot, this is the picture that appears in my head. I see a surgical robot being more like this, being these devices where you have that like tentacle-like, super small yet super dexterous robot system alongside surgeons that all work hand in hand to benefit a patient, right? By approaching a surgical procedure with unprecedented minimal trauma through a keyhole. That's the picture that comes in my head Obviously, that's not reality yet, but this is what I would like to see, and this is driving a lot of my research. And I also want to show you this scene from the movie Transcendence. So when I saw this movie in 2014, I think, I was like, this is exactly how I think a surgical robot should look like and behave. What a great vision for how multiple continuum robots could perform an intervention through keyholes, right? At a super high level of autonomy. That's probably autonomy levels 5, right? It's all automatically controlled. The robot just knows where to go, what to do. There's nowhere in the room, no person in the room. People are just watching this robot to perform surgery. Well, I'm not necessarily sure if Johnny Depp should be in the driving seat here, but you know, it's a movie, so I guess it sold better for Johnny Depp being in it. But you can think of this being a great vision for how surgical robots should look like in the future. And you see, like, after a while, the patient is completely recovered, almost in real time. Obviously, also quite an advancement in the drugs that the robot is delivering. But still, so continuum robots that are not necessarily relying on any natural pathways, but can actually reach into the body through any keyhole, that's quite a great vision, I think. And obviously, when you look at continuum robotics research, there is a vast amount of research that has been performed over the past decades. This is just showing some of the work. So if your work is not captured on the slide, I'm sorry, I'm just giving like a quick overview showing there is vast majority of the works going on like building small scale parallel robotic instruments that are very small, fetoscopic surgery that we have seen, the Eden 2020 project in Europe that was quite successful. Many work has been done on catheter steering and improving the performances. We've seen the StiffLab project as one of the bigger European projects. A lot of work has been done at Vanderbilt University. And so when we look at this vast majority of work, we also must be honest with ourselves, a lot of this is still on the benchtop, right? There might have been an animal experiment. There might have been like a few cases where these robots have been used on the pathway to surgery, but not that much. There are a few companies that are trying to commercialize some of these more sophisticated continuum robots like Titan Medical or Virtuoso Surgical, but we're still not there where that vision leads us. We've seen a lot of this progress, and I'm just showing the robot system that we have been building over the past decade. As the field matured, there exist really many different concepts on how to build continuously bending robots. This has happened to be the one that got me most excited about continuum robotics about 10 years ago. It's the concentric tube continuum robot, which is also sometimes called an active cannula or a tubular continuum robot. This mechanism design was originally proposed by Bob Webster and Pierre Dupont independently in 2006, both presented on the same concept at IROS. And here you can see our latest prototype in action, where multiple concentric pre-curved superelastic tubes are used to build what is known to be the world's smallest continuum robot. I know this gets pretty close, I think, at least in terms of appearance to what we have seen in that movie scene. Yet none of those concentric tube robots, even though they have been around for like almost 15 years, has ended up in a clinical setting, right? And I would like to take the next couple of minutes to think about why that is. And I'm starting at myself. So when I look at the approach that I took for very many years, in my research, is that I have been approaching surgical robotics naturally top-down, as most of us do, right? We are discussing with our medical collaborators, we identify an application with them, they're super excited about what we may help them with. There may be an existing surgical approach which could be improved, for example, by using a different surgical approach, or by using a continuum robot, which would allow them to take a different route to a location. And here on this slide, I'm just showing two examples from my postdoc time when I started working on continuum robots in Bob Webster's lab at Vanderbilt. That was that time when Caleb Rucker had just published a model that was using coast-rod theory on elastic rods. It was fairly accurate. And so we started looking into what can we do with these robots now that we are able to model them. And so we had great collaborators, one which was super excited about transnasal surgery, reaching the pituitary, which is often a location for benign tumors, which may cause a patient to get blind because it happens to, this growing tumor happens to press on the optic nerves. And so we thought, wow, that could be great. We could help surgeons to reach that location transnasally using a concentric tube robot. So we have built this bimanual robot system. We've deployed it in a cadaver, and we're looking at how can we teleoperate the robot? How can we actually reach the pituitary gland? We did some great research publications back then, but never ended up anywhere, which I feel is really sad because the potential is still there. But yeah, obviously all the advancement we have made were probably not enough. And the same holds on the intracerebral hemorrhage evacuation work that we have been doing, which was also a great project because we were thinking about, once a stroke patient has an intracerebral hemorrhage, we could use a steerable cannula, right, a concentric tube robot, to enter that location through a little burr hole, move the robot forward, and then aspirate this blood clot from within to reduce the pressure on the brain and hopefully have the patient recover sooner. So through all this endeavor, we implemented a real-time version of the kinematic model. We derived the differential kinematics for this robot, developed these robot prototypes, looked at teleoperation, human-machine interface, image feedback to automate parts of the procedure. So there was actually a lot that we have been achieving also in terms of fundamental advancements in concentric tube continuum robot. Multiple papers. This is just a small selection of it. But it never ended up at this for that surgical motivation we had in mind. And all these like fundamental research was always like hidden in these journal papers which were addressing the medical application. So when I'm coming back to how I would like to use these robots in surgery, I must really say we are just not quite there yet. Like continuum robots haven't helped a single patient yet, at least not the ones that are not catheters and bronchoscopes. So I personally would argue that one of the reasons that we mostly where that comes from is that we mostly approach this top down, right? So we are usually coming from the application, then trying to engineer, trying to do something that may help with this application. And while soft and continuum robots have a super high potential that is clear to almost everyone that sees them, it's also associated with quite a significant paradigm shift in terms of robotics, in terms of fundamental robotics research. So we are turning away from these rigid link structures that we have seen earlier to these jointless, compliant bodies that are fundamentally different. So also the research question that we ask are fundamentally different, and we might need to address them in a different way. We cannot purely focus on just this top-down research approach. So we might also look to the bottom-up way to solve many of these fundamentally different ways to treat a robot before we can actually come back to the surgical application. And in the following, I would like to give some examples on how we in my laboratory have been doing some of this more fundamental work over the past years to kind of fill the gap from the bottom. So turning away from that top-down approach, I am now looking at the robot specific questions that I could ask that would help from the bottom to reach that vision of continuum robots in surgery. And so I would like to start with this concentric tube continuum robot, as we happen to talk about this one already. So these concentric tube continuum robots are great. They are really small. So they're the smallest that exist. They have diameters down to 0.5 millimeter when you look at the tubes. So that's great. But there are some fundamental questions that I feel have not been properly addressed. Like, one is concerned, for example, with how to design the tubes. So how can appropriate tube parameters be selected such that the desired workspace and also stiffness requirements from an application perspective can be fulfilled? And some other research questions are concerned with control, like how can we enforce shape constraints on these robots? How can we achieve sub-millimeter accuracy with such a robot? These are questions that haven't been solved yet. And I would like to talk about those two on the next slides. So when we look at concentric tube continuum robots, there's this fundamental principle that is underlying how they work. So they are composed of these super elastic tubes, nickel titanium tubes, that are nested inside of one another. And there's two interaction principles that are utilized. First is you have a stiffer outer tube, for example, the straight one, and a pre-curved inner tube. So when you put them inside of each other, right, the inner tube, the less stiff one, will conform to that straight configuration naturally. And once you extend it from that straight tube, it will take on its pre-curvature again. Now on the right here, you see if you had two pre-curved tubes that you combine them with each other, so you nest them inside of each other, they will conform to an energy minimizing equilibrium, so to some combined curvature. So these two principles are then used in this robot to achieve motion. So here you see the robot is composed of 3 tubes. You might tell there's 3 tubes here at the tip. And now we can start extending these tubes from one another. We can start rotating these tubes. And by this axial or linear insertion and retraction and this axial rotation, we can make this robot conform to any possible shape that is achievable by these pre-curved tubes. Obviously, you might tell already, well, this is very much dependent on how you pre-curve these tubes. So not any tube pre-curvature can lead to any shape of the robot. So you will need to carefully pick how do you pre-curve these tubes, how many do you put inside of each other, and you also have to keep in mind that once they are nested inside of each other, they will conform to a common shape based on energy minimization. So the interaction of these tubes and how to select these two parameters is actually pretty hard. So that's why there has been a lot of research on computational design optimization. And here I'm just summarizing some of the work that Josephine Grana did in my lab during her PhD, where we were looking at how can we optimize over all these parameters of the tubes, like the inner diameter, the outer diameter, the length of the curved section, the curvature of the curved section, as well as the elastic modulus. And how can we then also optimize these tubes under multiple objectives? And these objectives, we have treated them knowing that we have a medical application in mind, but pretty general, like in terms of, for example, seeking to maximize the workspace of the robot while trying to make the robot sustain certain external forces without deflecting too much. And then she has been working on a computational design framework such that we came up with a particle swarm optimization process, which can work with multiple competing objectives, like this maximizing workspace and trying to make the robot as stiff as possible, which are contradicting. And so she has been implementing and testing this out on various occasions. And this is just showing the output of such an optimization scheme, where she had 50 particles, a random initialization of the algorithm. And then here you see, so as the workspace increases, as you have a higher workspace, the robot will also be less stiff, obviously, and so it will be more prone to deflection if you applied a force at its tip. So the stiffer the robot, the less it will be subject to external forces, the smaller its workspace. So you can see what builds here is a typical Pareto front of these two competing objectives. So any of the red dots will be a solution, and you will need to pick one that fulfills your application requirements to some extent. Now, this may be still very abstract, so I'm going to show you some results. Self-critical as I am, we have been looking at one of my previous publications in computational design optimization. So we have just plugged in the 2 parameters that I optimized for this transnasal surgery case that I have been showing earlier. And so we computed these objective functions. This is the workspace. So 70 square centimeters is the workspace of this robot. And this is the average deflection that the robot experiences when I put 1.5 Newton at the tip, which is quite typical for transnasal surgery. And you see in gray is the robot in its undeflected state and in blue in its deflected state. So you see the robot is deforming quite a bit when it's subject to external forces. So while I have been publishing this paper and saying, oh, computational design optimization is great, we can optimize these 2 parameters to fulfill these workspace requirements, back in the days, I was not considering that external forces would be deflecting the robot. So now, with this new optimization framework that we have been developing, we are now able to build a robot that is performing much better because the optimization framework is considering many more parameters. So here you see a robot that was optimized for the same application with a much larger workspace and much less average deflection under load. So that's quite a remarkable advancement in terms of choosing optimal 2 parameters. Because now we're not only optimizing over like a few parameters like I did back in the days, now we are optimizing over 13 parameters, namely the tube's curved lengths, curvatures, inner, outer diameters, and elastic modulus at the same time. So that's obviously a good advancement that could now help to also make these robots more suitable for some surgical applications. And we've also been looking at enforcing shape constraints. That was some work that one of my PhD students, Sven Lilge, is doing, where we have been looking at, well, can the robot actually enforce a shape constraint on its shape while it's performing a task at the tip? Here, the robot is following a circular trajectory, and we are trying to enforce that location back here to stay at this position. You could think of, okay, back here, I don't want the robot to move that much while it is following this task at its tip. And we have been making quite some advancement here, published this last year at ICRA, and are still preparing a journal paper on some of the results. But bottom line is it's possible, yet it requires a lot of insight on the 2 parameters in order to see which shapes can be attained. And then lastly, on concentric tube robots, we have also been looking at how can we perform, or how can we actually use this robot to achieve micro motions in terms of how accurate can we actually be. What we did here is we deployed a CTCR robot under a surgical microscope. Here it's used alongside with a chicken breast, where we put like 10 positions that we would like to reach. So we track those positions in the stereo images and also track the tip of the robot. Here it's with a spherical marker to make things a little easier. And then we asked our visual servoing scheme to servo the robot to these particular locations. And we were quite impressed ourselves that the error we were obtaining, measured in the medical images, was below 0.2 millimeters. So that was quite remarkable, because I think we were ourselves not thinking that the robot could be that accurate. So that was quite promising. So what we are currently working on is not just tracking the position of the robot, but also the orientation. And just recently, a student of mine made great advancements in markerless position and orientation tracking of the robot, such that, I look forward to see where this goes. But it was extremely promising to see these accuracy possibilities. Now, taking a step back again, coming back to the idea of approaching that from the bottom. So we have been talking about the concentric tube continuum robot, but there's also a lot of robots that are not relying on concentric tubes, because it's obviously quite limiting. While it can be very small, you are also limited in terms of what the robot can do. So many more continuum robots are actually composed of of a flexible backbone alongside a couple of tendon routing discs, such that pulling and releasing a tendon tension can make the robot bend. These robots are usually a little larger, like usually above 5 millimeters-ish. It's harder to build it smaller. And so we have also been working on tendon-driven continuum robots quite a bit. And we're also wondering, like, how can we design such a tendon-driven continuum robot such that it becomes deployable with multiple bending sections? And also, how can we use this robot to follow the leader? When you think about entering the human body, there's usually some tortuous path, some curvilinear path that you will need to follow. So we have been thinking, how can we actively steer such a robot along such a path, which is in contrast to the catheters that are relying on that tubular structure they are moving in. And back in 2014, we came up with this very neat idea of building an extensible tendon-driven continuum robot, which can be really short at the same time and it extend to full length. And you can see here, so there's this flexible backbone in the center. It's a nickel titanium tube composition. And then you see these tendon routing discs, and the red threads here are the tendons that are used to apply tension on these individual segments. You might already see that they look somehow suspicious. These tendon routing discs look a little weird, and that is part of the design feature. So these tendon routing discs are equipped with permanent magnets, and they are floating along the backbone here, but they, well, distribute themselves because the magnets are deployed at alternating polarity orientation, so they repel each other, such that however long that segment is, when I extend or contract it by changing the lengths of the tubes inside, they will distribute themselves pretty nicely. And so this concept can then be used to build a tendon-driven continuum robot with multiple of these extensible segments, which we can see here in this video. So we see this robot is composed of 3 individual bending segments. They all have a length that can vary between 15 and 70 millimeters, and the diameter of this robot is 7 millimeters. And so here you see this extension and contraction of these individual segments, which can come in very handy for various applications, not only in medicine, but also in maintenance, repair, and operations, for example. So looking at this robot, we have also been looking a lot into how can we model this tendon-driven continuum robot. And now there have been various models proposed for tendon-driven continuum robots. Believe me, there have been multiple publications, all very different in terms of their approach. So what we have recently been doing is undergoing the adventure of writing a paper that unifies the notation of all these models and makes suggestions on which one to use for your tendon-driven continuum robot. It's just in revision, so I think we're going to finish the revision by the end of this week, and hopefully we're going to see it published early next year. I think it's going to be very helpful for a lot of people in the community to choose a good model. So what we have been looking at is how can we differentiate the way that we represent the shape of the robot or represent the state space of the robot. And one simple way to do it is using a pseudo-rigid body model, right? Like a 3R model, by approximating the backbone as a 4-link serial manipulator, such that the state space itself is of dimension 4, like these 3 theta variables here, in addition to phi, which is defining the bending plane of one segment. This model has merit. In some cases, we were able to show that it might actually perform extremely well, particularly as you can also consider forces that are acting on these individual small segments. But the much more common way that we have seen in the literature, and probably many of you are familiar with, is the constant curvature representation of segments of the robot, where you approximate the robot as a series of constant curvature arcs, such that the arc parameters, like the radius or kappa, phi, the bending plane, as well as the length of the segment, can also be defined in a relatively small state vector. Yet this assumption of constant curvature only holds for some robot designs and can usually not account for external loads that are acting out of plane. So what we see much more often is this assumption of variable curvature along the robot, where we describe the position P and the attached frame R along the whole length of the robot, along the arc lengths parameterized by S. And so the robot backbone then undergoes elastic deformations while it experiences small strains. We can model the backbone as a beam. It undergoes linear elastic deformation where the stress is experienced by the backbone, and then that's linear proportional to the strain. And this change in state can then be completely specified by keeping track of the orientation of these directors relative to their orientation prior to the deformation. This can all be related through strain variables using continuum mechanics, particularly the Koszrad theory of elastic rods, to establish then a set of differential equations to relate the actuation parameters with the actual shape of the robot. Now, by just telling you what we do in this case, right, you will have noticed that the complexity is increasing quite a bit from here to here, which makes the whole modeling of continuum robots rather cumbersome. But luckily, we and many fellow continuum roboticists around the world have made significant progress in modeling. And as of today, we can state that these robots can be modeled reasonably well in terms of accuracy. And these are just showing two example robot types, the concentric tube continuum robot over here and the tendon-driven continuum robot over here. And we see the tip error and the occurrences, so histograms of the tip error in millimeters over experiments with 80 configurations or 180 configurations. And you see that for both robot types, the performance is similarly well. We see the highest occurrence of errors around the 1 and 2 millimeter range, which translates into the rule of thumb of 1.5 to 3% error with respect to length for a continuum robot. So if the robot was 300 millimeters long, right, the tip error became 4.5 to 9 millimeters, which might sound like a lot, but when you think about the modeling efforts we have to put in, it's actually quite well done, because now we can obviously use some sensors, some visual feedback, servoing of the robot to get down to the sub-millimetric accuracy that I was showing earlier. Nevertheless, we have to live with a robot that is typically an order of magnitude less accurate than an industrial robot arm. Another way to approach the model-based domain is something that we have been recently been working on quite a bit by comparing a model-based approach with a data-based approach, right? So rather than trying to model all the physical effects that the robot is experiencing in its compliance and in its elasticity, another way we could go about it is just investigating how a machine learning approach could help us to improve that modeling accuracy, right? We could collect data and observe where the robot tip is located in space using an electromagnetic sensing coil, for example, at the tip, collecting hundreds, thousands pairs of actuator of joint space parameters and end effector poses, and then feeding this into a neural network and hoping that this would implicitly consider all these unmodeled effects that we have not been able to capture in the model itself. For example, friction has typically not been modeled because it makes the model even more complex. And so we did some of this. This is just showing some of the work that my PhD student Reinhard Grassmann has been doing. So, and the results that he got were pretty remarkable for the forward kinematics. It's rather than this 1.5 to 3% with respect to length, he got the modeling accuracy down to below 1% with respect to length. So there's definitely merit in investigating the model-based approach more in terms of knowing if we probably considered more of the physical effects, we could probably get this down to below 1% as well. So it's just recently something we have been trying to investigate. even though I also see that there are limitations to machine learning approaches for sure. Like it's not solving the problem of not being able to model the robot well, because the data-based approach can only know as much as the data tells it, right? Anyway, so that's an interesting route that we have been taking recently, and I'm looking forward to see where that leads us. But yeah, then we can use this information of the model, whether it's derived data-based or model-based, to have our robot perform follow the leader motion, not on any paths, just on paths that are composed of a similar number of quasi-constant curvature segments. But then the robot can actually make this follow the leader motion also within any environment, which is a great prerequisite when we think about medical applications. So that's a great fundamental result that we have been making by looking at this model-based open loop controller, which gets the robot along a desired path. So in some of our ongoing future work, we are definitely integrating sensor feedback and going to try to integrate this with teleoperation. But yeah, so there has been quite some progress on tendon-driven continuum robots. And so the last thing I would like to touch upon before finishing up the talk is the notion of embracing the compliance of a continuum robot. Like when you see here, this is a feature, but could also be a bug, right? So the robot is compliant, meaning it's deforming as soon as it's subject to external forces. This can be great. It makes them very versatile and safe to use close to or even within a human, because right, compliance is very helpful, but also very challenging. Any force acting on this robot will deform it quite a bit. And in the soft and continuum robotics community, we agree that it can be an asset, as this compliance can be used to implement embodied intelligence, right? So the robot in itself could make use of that morphological computation. So yet in a medical context, that can be very, very challenging. And so how to achieve variable stiffness in a continuum robot and how to overcome challenges that are arising from compliance is quite a huge research endeavor, I think, that we in the soft and continuum robotics community are still about to solve. Like there's, I think, still a lot of research to be done. We have been looking at it from a mechanical perspective in terms of, well, how can we, from an engineering side, help to overcome some of the challenges by developing a stiffening sheath that we would put around the robot and then apply. In this case, it's a vacuum which causes these individual scales here to press on each other, and the friction would cause the whole sheath to stiffen up. So it's layer jamming as the principle that we're utilizing here. And so you could think about something like the stiffening sheath being put around a continuum robot. And so as soon as you want the robot to be stiff, you could just engage the sheath. It would stiffen up such that your robot would not be subject, or would not be deflected as it's subject to external forces. Well, but in terms of dimensions, right, that's probably larger than we wished it would be. There's probably some potential to make it smaller, but nevertheless, for some applications, it may be useful. And now I'm trying to come back to the surgical side. For example, in this project that we did with the medical school in Hanover with the Department for Urology, we have been thinking about ways how to build a port for laparoscopic surgery that can be changed in terms of its curvature to approach an organ from multiple viewpoints through a single port, like through the navel typically. And so one of my PhD students, Erna Amanov, for his dissertation, developed this endoport system here, which is composed of a tendon-driven robot and then also enclosed with this stiffening sheath that I have been showing on the previous slide, such that it can then be used through the navel in a single port setting, such that this port system could allow for multiple pre-curved instruments to be deployed through the single port. The port can be stiffened as soon as it approached the site of interest, and then through these working channels, additional continuum robot arms could be deployed, which have yet to be developed. And then there's also some frontiers in terms of where can embracing the compliance go. Like we have been doing some work on focusing on having these robots collaborate with each other. And this is just a small collection of things that we're doing. For example, here in collaboration with Taha, and in a joint project that we even have between University of Toronto and CNRS, paying for travel between us, which unfortunately cannot happen. But still, we are working still together as good as we can in thinking about how can we use a dual arm concentric tube robot such that the two arms can follow a primary task and the other could perform a secondary objective, for example, keeping a constant distance or keeping a proper orientation to the other one. So that's pretty cool work. And I think by investigating more how secondary or even tertiary control objectives could help, we could probably also mitigate some of the challenges that we have from compliance. And another research area that I recently got really excited about are parallel continuum robot structures. That's a project we started back in Hanover with Professor Oudmayer's group shortly before I left. So we continued collaborating together, which is now making use of simpler tendon-driven continuum robots that we use together in a parallel mechanism in hope that we can benefit from the structural advantages of a parallel structure, while at the same time having still the lightweight and the compliance inside. And this is just a planar prototype that we have been building and publishing this year. And this is the spatial prototype that we are hopefully going to show next year. Ral was luckily just asking for a revision about a few days ago, so I'm confident to show you some of that work. That's a spatial version of the same principle. And now you could think of these robots being potentially used in a medical application, right, where they would come in through multiple small ports, connect to a common platform, and we might be able to utilize the compliance as well as the dexterity. Not only in medicine, this is also a great possibility for inspection tasks. Okay, approaching the 10 o'clock mark, at least here, for you it's 4. Concluding my talk, so I have been arguing that bottom-up research is also needed to advance the current state of the art in continuum robotics and to address some of the fundamental challenges that soft and continuum robots are facing in order to get these robots to a clinical application. We have been seeing these 3 different robot types, which have huge potential, for example, for microsurgery, for transluminal surgery, or for abdominal surgery. So we have been seeing in our studies that submillimetric accuracy may in fact be achievable if we applied it in a good control scheme. We developed mechanisms that would allow us to deploy tendon-driven continuum robots along curvilinear path. And we have been trying to address these stiffness issues and collaborating continuum robots to overcome compliance. Now, there's still a lot of work to be done. Like, now we have to meet back up with the top, right? Like get this now back rolling in terms of a medical application. And also still facing a lot of challenges in terms of human-robot interaction, like limited sensory perception or limited situational awareness, how to increase autonomy levels and how to realize human-robot interaction effectively. There's still a lot of work to be done, which is good. I'm in the middle of my career, so there's still a lot of tasks I can follow along, which is great. And yeah, hopefully my vision of having a continuum robot alongside surgeons, like I've shown earlier in the picture, can become reality at some point. This brings me to the end of my talk. I have been very fortunate to work with brilliant student and postdocs over the past decade, some of which you can see here. And it's really their hard work and their dedication that led to all the innovation and advancements that I was able to present today. So big shout out to all these people. I would also like to acknowledge the funding agencies that make this research possible. And lastly, I would like to say that after moving to Canada last year, I'm still actively looking for new collaborators and, more importantly, ways to stay connected to Europe, because in my heart, I'm a European. So if you happen to look for a collaborator, if you feel like, oh, Continuum Robots maybe the thing to go, I would like to collaborate with any one of you. If you happen to know a student of yours who is seeking for an opportunity abroad, send them my way. I'm happy to host anyone who's eager to work on all these cool problems.
Thank you very much, Jessica. Thank you for this great overview about Continuum Robots and for this storyline that you gave, like along with very significant scientific achievements. We probably have some time for questions. The first question came from Jérôme Chefchik from ISIR in Paris. So he was asking how we can define dexterity of Continuum robots. What are actually the criteria that matter when comparing different Continuum robots? That is diameter, curvature, external footprint, the diameter ratio.
That's a great question, Jérôme. I'm glad you're asking. It's actually something we are scratching our head around this whole summer in how to define dexterity in a Continuum robot. Because the classical formulation of dexterity in a serial arm manipulator or also in a parallel robot may not be sufficient, because we might also want to express the ability of the robot to change its shape, so its ability to rapidly change shape at the same time. I don't have a good answer for that one, but I can tell you we're working on it, and I'm happy to discuss it.
Yeah, and another question from Isir, I think, if I did not mistaken, about Félix Péchereau, and also from Jocelyne, but both of them are related to the contact forces. So they were wondering how, like all the examples that you have shown deal with free space robots. So what happens when there's contact forces? How can we close the loop? And Jocelyne was wondering if we know, if the environment is quite structured, how we can use this knowledge inside the control loop.
Yeah, that's definitely a challenge. So the good thing is the models that we have can handle forces acting along the robots anywhere. So from a modeling perspective, at least, we can describe the state under external forces. And so that's a good thing. But the question of, are we able to sense these and are we able to localize these? That is still ongoing and an ongoing challenge we are facing. Like, there are certainly ways to go about it. There has been some work where we have been looking at, okay, if we have discrete information along the robot lengths, like let's say an electromagnetic tracking call at the tip and somewhere along its lengths. So if we measure a deviation from the model state, can we use that to reason about what forces have been acting on the robot? Obviously, that's not real-time capable, so may not be super helpful. I think probably the way to go is here that the possibility of measuring the strain along the robot using fiber break ratings, for example, may be really the way to go. So you would be able to measure the strains along the length. From the strain information, you can get the shape, and then we are hopefully able to use this information to more effectively close the loop. But yeah, it's not an unsolved dilemma. I think there are some great ideas on how to go about it, but certainly an issue. Like, there's always this this challenge of make your robot as flexible and as elastic as possible, but not too much, right? That deformation would not happen in a way that would impede your application. But that's certainly one of the endeavors we are trying to do. Like, if the lab wasn't closed this summer, I wish I would be further along. That's definitely something we are working on. Pretty many people are working on, probably some of you as well. So
it's like what you've just said about the bug and the feature. One of them can be the other at the same time. Yeah, so maybe a last question from Sandrine Vos from Team C in Grenoble. She was asking what would be the maximum feasible length of continuum robot today, knowing that all the friction that you said that was not yet modeled and the maybe torsional instabilities that would occur for this kind of robots.
Yeah, thank you for the question, Sandrine. That's so the typical length that we have been building, which are manageable, is about this 20 to 30 centimeters. So that works well. At that very small scale, like it's just always a mechanical dilemma that we're facing, right? We can certainly build a little longer. Like we have been recently building an origami style robot, which is 60 centimeters long, which is super lightweight, so it can maintain its weight, but obviously suffers from other issues. We hope to see it next year at the Soft Robotics Conference. So yeah, I think everything 30 centimeters is fine, but also from coming back to the surgical standpoint, right, 30 centimeters is quite a good length. Like when you think of your head dimensions, 30 centimeters may be really long enough to get everywhere. So yeah, 30 centimeters is probably a very feasible length today.
Okay, I do not see any other questions on the YouTube broadcast. So I would like to thank you again very, very much, Jessica, for your overview and for your time and sharing all these exciting results with us. And
my pleasure.
Very welcome to stay to the end of the day if you have some time later.
Absolutely.
Thank you very much.
Thank you all for joining my talk.